Article 406.9 of the 2001 California Electrical Code, which is based on the 1999 National Electrical Code, addresses ground fault circuit interrupters, or GFCIs. Specifically, 406.9c covers equipment supplied by GFCIs and states that equipment shall not be supplied from a GFCI unless the protected equipment is located within the zone of protection as defined in 406.4d2. Additionally, 406.9d mandates that a test button be provided to test the ground fault protection system, and when operated, the test button shall cause the GFCI to open and shall prevent circuit power from being supplied to equipment connected to the GFCI. In the described scenario, connecting the outside GFCI receptacle to the load side of the garage GFCI creates a code violation. Firstly, the outside GFCI is not within the zone of protection of the garage GFCI. This means that a ground fault in the protected zone of the outside GFCI will not reliably cause it to trip. This compromises the intended safety function of the GFCI, potentially creating an electrical shock hazard. Secondly, the test button on the outside GFCI is not functioning as intended. When pressed, it should only interrupt the power to the devices connected to that specific GFCI. The test button should not be tripping the upstream GFCI. The fact that it is tripping the interior garage GFCI indicates an improper wiring configuration. To correct this issue, the outside GFCI needs to be wired so it has its own dedicated supply. Each GFCI is designed to protect the wiring and equipment downstream of it. A GFCI works by monitoring the current flowing into a circuit and comparing it to the current flowing back. If there is a difference, even a tiny one like 5 mA, it indicates that some of the current is leaking to ground, which could be through a person. The GFCI trips the circuit very quickly, within milliseconds, to prevent electrical shock. A standard circuit breaker only protects against overloads and short circuits, not ground faults. Therefore, in areas where water is present, like bathrooms, kitchens, and outdoors, GFCIs are required to protect people from electrical shock hazards. Understanding the proper wiring and operation of GFCIs is crucial for electrical safety. By adhering to the NEC guidelines, specifically Article 406.9, electrical installations will ensure that these devices function correctly to protect against ground faults. When installing GFCI receptacles, several key factors must be considered to ensure proper operation and safety. Firstly, identify the line and load sides of the GFCI receptacle. The line side connects to the incoming power from the breaker panel, while the load side provides protected power to downstream receptacles or devices. Incorrect wiring can lead to the GFCI not functioning properly or creating a safety hazard. Secondly, ensure that the GFCI receptacle is properly grounded. Grounding provides a path for fault current to flow back to the source, allowing the GFCI to trip and interrupt the circuit. A missing or improper ground can render the GFCI ineffective. Thirdly, when wiring multiple receptacles in a circuit, determine whether they should be GFCI protected. If protection is desired, wire the additional receptacles to the load side of the GFCI receptacle. However, be aware that any problems with wiring or devices downstream can trip the upstream GFCI, potentially causing inconvenience. Fourthly, always test the GFCI receptacle after installation using the test and reset buttons. The test button simulates a ground fault, causing the GFCI to trip and cut off power. The reset button restores power to the circuit. If the GFCI fails to trip when tested or cannot be reset, it indicates a wiring problem or a defective GFCI receptacle. Fifthly, be aware of local electrical codes and regulations. These codes specify where GFCI protection is required and outline the proper installation methods. Failing to comply with these codes can result in fines or safety hazards. Sixthly, consider the environment where the GFCI receptacle is installed. Outdoor locations and damp environments require weather-resistant GFCI receptacles and enclosures to protect against moisture and corrosion. Seventhly, when replacing an existing receptacle with a GFCI receptacle, carefully disconnect the old receptacle and identify the wires connected to it. Use a voltage tester to ensure that the circuit is to energize before working on it. Connect the wires to the corresponding terminals on the GFCI receptacle following the manufacturer's instructions. Eighthly, avoid overloading the circuit protected by the GFCI receptacle. Overloading can cause the circuit breaker to trip, interrupting power to the GFCI receptacle and any downstream devices. Determine the total load of the devices connected to the circuit and ensure that it does not exceed the circuit's capacity. Ninthly, regularly inspect GFCI receptacles for damage or wear. Cracked or broken receptacles should be replaced immediately. Also, check for loose wiring or corrosion on the terminals. Tenthly, if unsure about any aspect of GFCI receptacle installation, consult a qualified electrician. Working with electricity can be dangerous, and improper wiring can lead to electrical shock or fire. A qualified electrician can ensure that the GFCI receptacle is installed safely and correctly. When dealing with GFCI tripping issues, a systematic approach can help identify the cause. Firstly, determine if the tripping is nuisance tripping or a genuine ground fault. Nuisance tripping can be caused by minor current fluctuations or electromagnetic interference. If the GFCI trips frequently without any apparent reason, it may be due to nuisance tripping. Secondly, inspect the wiring and devices connected to the GFCI circuit. Look for loose connections, damaged insulation, or faulty devices that could be causing a ground fault. Pay close attention to areas where water may be present. Thirdly, use a GFCI tester to check the tripping current of the GFCI receptacle. A GFCI tester simulates a ground fault and measures the current required to trip the GFCI. If the tripping current is outside the specified range, the GFCI receptacle may be defective. Fourthly, disconnect devices one by one from the GFCI circuit to isolate the source of the tripping. If the GFCI stops tripping after disconnecting a particular device, that device is likely the cause of the problem. Fifthly, check for shared neutrals and multi-wire branch circuits. A shared neutral can cause current imbalances that trip GFCIs. If a shared neutral is suspected, separate the neutral conductors and test the GFCI again. Sixthly, be aware of the limitations of GFCIs. GFCIs protect against ground faults, but they do not protect against overloads or short circuits. If the circuit breaker trips frequently, it may be due to an overload or short circuit, not a ground fault. Seventhly, if the GFCI tripping issue persists, consult a qualified electrician. A qualified electrician can perform a thorough inspection of the electrical system and identify the root cause of the problem. They can also recommend appropriate solutions to prevent future tripping. When troubleshooting GFCI problems, it's important to prioritize safety. Always to energize the circuit before working on any electrical component. Use insulated tools and wear appropriate personal protective equipment. If unsure about any aspect of electrical troubleshooting, consult a qualified electrician. Understanding the concepts of grounding and bonding is essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing protective devices like circuit breakers and GFCIs to trip and interrupt the circuit. Bonding connects all metallic parts of an electrical system together to create a low impedance path for fault current. Firstly, the grounding electrode system consists of a grounding electrode, such as a ground rod or ground plate connected to the neutral conductor at the service entrance. The grounding electrode provides a connection to the earth, allowing fault current to flow back to the source. Secondly, the equipment grounding conductor connects the metallic parts of electrical equipment, such as enclosures and conduit, to the grounding electrode system. The equipment grounding conductor provides a low impedance path for fault current, ensuring that metallic parts do not become energized during a fault. Thirdly, bonding jumpers are used to connect different metallic parts of an electrical system together, such as metal water pipes and gas pipes. Bonding jumpers ensure that all metallic parts are at the same electrical potential, reducing the risk of electric shock. Fourthly, the neutral conductor carries the unbalanced current in a circuit back to the source. The neutral conductor is connected to the grounding electrode system at the service entrance. Fifthly, the ground fault circuit interrupter, or GFCI, is a device that protects against ground faults. The GFCI monitors the current flowing into a circuit and compares it to the current flowing back. If there is a difference, even a tiny one, it indicates that some of the current is leaking to ground, which could be through a person. The GFCI trips the circuit very quickly to prevent electrical shock. Sixthly, the arc fault circuit interrupter, or GFCI, is a device that protects against arc faults. An arc fault is an unintentional electrical discharge that can cause a fire. The GFCI detects arc faults and trips the circuit to prevent fire. Seventhly, surge protective devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. SPD divert excess voltage to ground, preventing damage to equipment. Eighthly, the National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems. The NEC specifies the size and type of grounding conductors, bonding jumpers, and other components. Ninthly, local electrical codes and regulations may also apply to grounding and bonding electrical systems. These codes may have additional requirements or restrictions. Tenthly, it's important to consult a qualified electrician when designing and installing grounding and bonding systems. A qualified electrician can ensure that the system meets all applicable codes and regulations and that it provides adequate protection against electrical shock and fire. Understanding electrical circuit concepts is crucial for anyone working with electricity. An electrical circuit is a closed loop that allows electrical current to flow from a source to a load and back. Firstly, voltage is the electrical potential difference between 2 points in a circuit. Voltage is measured in volts. Secondly, current is the rate of flow of electrical charge through a circuit. Current is measured in amps. Thirdly, resistance is the opposition to the flow of electrical current in a circuit. Resistance is measured in ohms. Fourthly, Ohm's law states that the voltage across a resistor is equal to the current flowing through the resistor multiplied by the resistance of the resistor. Mathematically, Ohm's law is expressed as volts equals amps times ohms. Fifthly, power is the rate at which electrical energy is transferred in a circuit. Power is measured in watts. Sixthly, series circuits are circuits in which components are connected in a single path. In a series circuit, the current is the same through all components, and the voltages add up to the total voltage. Seventhly, parallel circuits are circuits in which components are connected in multiple paths. In a parallel circuit, the voltage is the same across all components, and the currents add up to the total current. Eighthly, series parallel circuits are circuits that combine series and parallel connections. Ninthly, alternating current, or AC, is a type of electrical current that periodically reverses direction. AC is the type of current used in most homes and businesses. Tenthly, direct current, or DC, is a type of electrical current that flows in one direction only. DC is the type of current used in batteries and electronic devices. When working with electrical circuits, it's important to follow safety precautions to prevent electrical shock and fire. Always to energize the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment. If unsure about any aspect of electrical circuit work, consult a qualified electrician. Electrical safety is paramount when dealing with electrical systems and equipment. Electric shock can cause serious injury or even death. Fire can result from electrical faults or overloads. Firstly, always to energize circuits before working on them. Turn off the circuit breaker or remove the fuse that supplies power to the circuit. Use a voltage tester to verify that the circuit is energized. Secondly, use insulated tools and equipment. Insulated tools protect you from electric shock if you accidentally come into contact with a live wire. Wear appropriate personal protective equipment such as rubber gloves and safety glasses. Thirdly, never work on wet or damp surfaces. Water is a good conductor of electricity, and working on wet surfaces increases the risk of electric shock. Fourthly, be aware of overhead power lines. Keep a safe distance from overhead power lines when working outdoors. Fifthly, never overload circuits. Overloading a circuit can cause the circuit breaker to trip or the wiring to overheat, potentially leading to a fire. Sixthly, use ground fault circuit interrupters, or GFCIs, in wet or damp locations. GFCIs protect against electric shock by detecting ground faults and interrupting the circuit. Seventhly, use arc fault circuit interrupters, or RFCIs, to protect against arc faults. Arc faults can cause fires. Eighthly, inspect electrical cords and equipment regularly for damage. Replace damaged cords and equipment immediately. Ninthly, never tamper with electrical equipment or wiring. Only qualified electricians should perform electrical work. Tenthly, if you experience an electric shock, seek medical attention immediately. Even a minor electric shock can have serious health consequences. Familiarizing yourself with the National Electrical Code can help you understand what it takes to install electrical wiring safely. Chapter 1 of the NEC covers general requirements like these. Article 90 contains information about the purpose, scope, and enforcement of the NEC. Article 100 contains commonly used definitions. Article 110 contains requirements for electrical installations. Chapter 2 of the NEC covers wiring and protection and contains information about the use and identification of grounded and grounding conductors. Article 200 covers the use and identification of grounded conductors. Article 210 covers branch circuits. Article 215 covers feeders. Article 225 covers outside branch circuits and feeders. Article 230 covers services. Article 240 covers overcurrent protection. Article 250 covers grounding and bonding. Chapter 3 of the NEC covers wiring methods and materials. Article 300 covers general requirements for wiring methods. Article 310 covers conductors for general wiring. Article 312 covers cabinets, cutout boxes, and meter socket enclosures. Article 314 covers outlet boxes, device boxes, pull boxes, junction boxes, conduit bodies, and fittings. Article 320 covers armored cable, type AC. Article 330 covers metal-clad cable, type MC. Article 334 covers non-metallic sheet cable, types NM, NMC, and NMS. Article 340 covers underground feeder and branch circuit cable, type UF. Article 350 covers flexible metal conduit, type FMC. Article 352 covers rigid polyvinyl chloride conduit, type PVC. Article 358 covers electrical metallic tubing, type EMT. Article 366 covers auxiliary gutters. Article 370 covers cable trays. Chapter 4 of the NEC covers equipment for general use. Article 400 covers flexible cords and cables. Article 404 covers switches. Article 406 covers receptacles, cord connectors, and attachment plugs, or caps. Article 408 covers switchboards and panel boards. Article 410 covers luminaires, lamp holders, and lamps. Article 422 covers appliances. Article 430 covers motors, motor circuits, and controllers. Article 440 covers air conditioning and refrigerating equipment. Article 445 covers generators. Article 450 covers transformers and transformer volts. Article 455 covers phase converters. Chapter 5 of the NEC covers special occupancies. Article 500 covers hazardous, classified locations. Article 501 covers Class I, Division 1 and 2 locations. Article 502 covers Class Roman II, Division 1 and 2 locations. Article 503 covers Class Roman III, Division 1 and 2 locations. Article 504 covers intrinsically safe systems. Article 505 covers Zone 0, 1, and 2 locations. Article 510 covers hazardous, classified locations, specific. Article 511 covers commercial garages, repair and storage. Article 513 covers aircraft hangars. Article 514 covers motor fuel dispensing facilities. Article 515 covers bulk storage plants. Article 516 covers finishing processes. Article 517 covers healthcare facilities. Article 518 covers places of assembly. Article 520 covers theaters, audience areas of motion picture and television studios and similar locations. Article 525 covers carnivals, circuses, fairs, and similar events. Article 530 covers motion picture and television studios and similar locations. Article 540 covers motion picture projection rooms. Article 547 covers agricultural buildings. Article 550 covers mobile homes, manufactured homes, and mobile home parks. Article 551 covers recreational vehicles and recreational vehicle parks. Article 552 covers auxiliary buildings. Article 553 covers floating buildings. Article 555 covers marinas and boatyards. Chapter 6 of the NEC covers special equipment. Article 600 covers electric signs and outline lighting. Article 604 covers manufactured wiring systems. Article 605 covers office furnishings, or fixed partitions. Article 610 covers cranes and hoists. Article 620 covers elevators, dumbwaiters, escalators, moving walks, platform lifts, and stairway chairlifts. Article 625 covers electric vehicle charging systems. Article 626 covers managed electrical energy storage systems. Article 630 covers electric welders. Article 640 covers audio signal processing, amplification, and reproduction equipment. Article 645 covers information technology equipment. Article 646 covers modular data centers. Article 647 covers sensitive electronic equipment. Article 650 covers pipe organs. Article 660 covers X-ray equipment. Article 665 covers induction and electric heating equipment. Article 668 covers electrolytic cells. Article 669 covers electroplating. Article 670 covers industrial machinery. Article 675 covers electrically driven or controlled irrigation machines. Article 680 covers swimming pools, fountains, and similar installations. Article 682 covers natural and artificially made bodies of water. Article 685 covers integrated electrical systems. Article 690 covers solar photovoltaic (PV) systems. Article 691 covers large-scale photovoltaic (PV) electric power production facility. Article 692 covers fuel cell systems. Article 694 covers wind electric systems. Article 695 covers fire pumps. Chapter 7 of the NEC covers special conditions. Article 700 covers emergency systems. Article 701 covers legally required standby systems. Article 702 covers optional standby systems. Article 705 covers interconnected electric power production sources. Article 708 covers critical operations power systems (COPS). Article 710 covers over 600 volts, nominal, general. Article 712 covers direct current microgrids. Article 720 covers circuits and equipment operating at less than 50 volts. Article 725 covers Class 1, Class 2, and Class 3 remote control, signaling, and power-limited circuits. Article 727 covers instrumentation tray cable type ITC. Article 760 covers fire alarm systems. Article 770 covers optical fiber cables and raceways. Article 780 covers communications systems. Chapter 8 of the NEC covers communications systems. Article 800 covers communication circuits. Article 805 covers communications systems. Article 810 covers radio and television equipment. Article 820 covers community antenna television and radio distribution (CATV) systems. Article 830 covers network-powered broadband communications systems. Article 840 covers premises-powered broadband communications systems. Chapter 9 of the NEC contains tables and examples. Tables cover conductor properties, conduit and tubing dimensions, and box fill calculations. Examples provide guidance on how to apply the NEC requirements to specific situations. Annexes are not part of the formal requirements of the NEC but provide additional information and guidance. Annex A provides product safety standards. Annex B provides application information for ampacity calculation under engineering supervision. Annex C provides conduit and tubing fill calculations. Annex D provides examples. Annex E provides optional calculations for dwelling units. Annex F provides available fault current calculation information. Annex G provides installation of overhead service conductors. Annex H provides administration and enforcement. Annex I provides recommended tightening torque tables. Annex J provides informational notes.